Sup guys, and welcome to today's show. Today we are gonna continue on with our virtual machine project. Uh, so this is basically the second episode, or third, depending on how you count the last one, which was a double episode. But last time we created the general structure of our virtual machine. So our virtual machine is basically a CPU and some memory at this point. And the memory is divided between a code section, which can be executed, and a data section, the stack. So this break line here defines where the one starts and the other ends. A CPU is a structure which basically, for now, only contains one thing, which is another structure, registers. And the registers are those. We have 4 general purpose ones for everything from addition to moving data around. Then we have the stack pointer and the instruction pointer. So that's the CPU, and the memory is just this 65K of bytes. And what we did last time, we defined a couple of instructions. We have the move, which puts a number inside of a register. We have the no-up, which does nothing, and we have halt, which ends the execution of our program. Okay, so what did we do last time in terms of functions? We created our main, which just tests our other functions. The virtual machine function will create it. This is a constructor function, which constructs a new virtual machine object or structure. We have a map function, which maps a instruction to how many bytes it takes, how big it is. And we have this temporary thing, that's why I have a space in the front of it, which just creates an example program. The execute function will go through a program and execute all the instructions. This will do the same, but only for one single instruction. And then we have error, which prints an error and exits. Okay, so that's what we have at this point. What is the logical next step? I would say doing something more with the move instruction, because at the moment it only moves something to AX, I believe. Let's see how we did that thing. Go into the C file and we go here. Yes, we are just changing the AX. But we do want to be able to change the other ones as well. And if you remember syntax for our move instruction, we have it in a comment somewhere. Here it is. So it's a 3-byte. It's a 3-byte instruction, and the first byte defines that it's a move instruction and also the register it will move it to. So the 1 to the right, least significant bit, is defining that it's a move instruction, and those 3 that follows will define the different types of registers that we want to move to, or possibly other things than registers. That's right. We will eventually be able to move stuff to data, to memory as well. So let's see. We need how many instructions? We have at least 5 registers that we want to move stuff to. So let's see. We will need all those 3 for that, I guess. Let's see. Let's say all zeros is the AX. A 1 here is the BX. A 1 and a 0 is CX. 2 1s, that is DX. A 1 here is SP. And that's basically it, right? So let's see. And maybe we will have some other register as well that we're going to move to. So let's say let's say we set all of these ones, all of these bits to ones. Let's say that means we are moving to memory address instead of a register. That way we can differentiate between them in a good way. Yeah, I think that's the best play. Right, so how do we achieve this? Let's see. This move instruction gets the opcode, which is, it's an enum. And from that enum, we will be able to, let's see, yeah, we will be able to check what register we want to move it to. We need to do something though. Let's say we have those 4 bits at the end. And this is a 1. Let's say all of these are 1s. What number do we get? It should be, right, if we have a 1 here and all zeros, then we would have 1, 2, 4, 8, 16. Okay, so it's 1 less, it's 15. So 15 is all ones, and that will be move to a memory address. So something like this. But we do also want to specify, let's see, no, this is good. So every instruction between 1 and 15 will be handled by this function, and that means we need to update our map. Remember our map, the one that maps between different So how can we have several numbers for the same enum? That's not possible. Let's see how we can achieve this. Maybe we shouldn't use an enum. Let's see, where do we have this? Where do we have this enum? So hard to find things in this code. There we have it. Okay, so we have move as one, no, we need to do this a little bit differently. But how? Well, I guess we will have to do something like this. Because I don't like having to do this. And I don't really want to add additional overhead either. Maybe we could add some kind of exception. So let's say we put a comment right here, and we say that this goes from 0, 1 to 0, 15. Which means we would need to rename this or revalue this to 10, and this would be 11 instead. Okay. So if we have this way of doing it instead, how will we deal with our map? This one. I guess we could, let me think. So we have move. I think we can add values here. So what if we were to do something like 0, 2, and that will also be 3 bytes. And we're gonna have several of those. So we have the 1, and then we have 2, 3, 4, 5. So that's the only thing changing is this thing. So let's do something like this. and we have 4, so we need 4 lines like this, and we don't need the last one. And then we just put the numbers in here. So this is 1 and 2, and we keep going like this all the way up to 15. So let's see, that is 4 and we have 5. We could make a function which checks for a range, but I don't want to mess up our system like that. I think it's, even if this looks intimidating, I think it will be easier in the long run if we have as simple as possible system. Okay, so basically if we give this map function any of the values from 1 to 15, it will return that it's 3 bytes. It's a 3 byte sized. That it's a 3 byte sized variable, or instruction rather. Okay, so what do we need to change to make this right? We don't need to do anything with the map function since we put all the logic in here. But we do need to think a little bit about our execute instruction function. So let's see. This one. Because currently what we do is first we switch the size. That will not be a problem. And then we switch for the value of move. So what we need, well, we could actually put the different cases in here. So there is a new feature in C. I read about it. I'm not sure if it's implemented, but I'm using the latest GCC, so perhaps that you should be able to do a range here. Something like this. I'm not sure about the syntax though. Let's try this out and see what it says. So let's compile this thing, and it gives us an error as anticipated. The first dot, though, it did not have any problems with. Interesting. But since I don't know the syntax and it's not too easy to find in manual pages, probably impossible. We will have to Google in this case, I suppose. But when you have to Google, just don't make it as broad as possible. Do something like, I want to search only GNU gcc.gnu.org for switch case ranges. Okay, it should be 3 dots. Okie dokes. Seems like we're on the right path here, guys. So let's put in the 3 dots in here. That's probably news to you as well, right? It was possible to do this in C++, but it has never been possible to do it in C. Yeah, it works. Nice. And this thing doesn't crash? No? Okay. That's good. That makes our lives a lot easier. And we will cover the entire range to 15. So basically, let's see. But maybe we are getting at this wrong, because I wanted to do this based on the rightmost significant byte, right? Maybe that's stupid. Let's see. Let's try to find that thing in here. Okay, so if we do it that way, then all of those bytes will be a problem. Because we want to use these for other instructions, right? And we don't want to block this one here. That will make our lives very complicated. So how to do that part in a better way? Maybe we could do the same thing, but we use this bit instead. And then we can use those 3 as we want. That's better, I think. And this is 8. So everything starting with an 8. Which means, do we have to do all of that stuff all over again? No, not really. Because we don't need let's see. We don't need the entire range. Why is it so hard to find stuff here? Alright, let's see. So this is 1, 2, 4, 8. So okay, everything started with an 8 all the way through to 15. So if you go back here, starting with an 8, that's this. So we can remove this line. And let's see. Let's remove this line and we start with 8 here instead. So we take 1 less at each position. And this should be, let's see. This was an E, so it should be a, what was it? Let's see, we have 8, 9, 10, 11, this should be C, this should be D, this should be E, and we add that last missing thing. Okay, this is a much smarter way to do it. So the only thing we are allocating at this point are everything from 8 to 15. So let's also update our map. We need to update this as well. So this will start at 8. 8 all the way to F. And where is our map? Or I don't mean our map, I meant it's our C function I'm talking about. Our map is done. Let's save it, by the way. So this is exec instruction. So what we want to check here is basically that we go from 8 to 15. Then we do the move function. So maybe we should move those two as well, because currently, let's see, currently we start at 8, go all the way to 15, and then we go from 10 here. It's better that we put those instructions in the beginning. So let's move these two up a little bit. No, that's not right. There. Now we need a comma, and this should be gone. This looks a little bit weird though. Okay, there we go. So now it's starting to look the way I want it to. And this range here. So now we only need to parse this information inside of this function. So what are we going to do here? Well, we're gonna have a switch statement at least, that's for sure. And we can switch on the opcode. And let's do this with binary so we know what we're doing. So let's just put a 0 here, and then above it we will put the binary representation. So everything will start with a 1, and then we will have 3 bits that we can do stuff with. So let's copy this. And how many combinations? We have 3 bits. 2 times 2 is 4, and 8. So let's put 8 of those, like this. And this will be, no, this will start at 0, so this will be 8. Then we get a 1 here, so we get 9. 0 and a 1 is 10. 2 ones 11. And perhaps we should keep using hexadecimal so we don't go away from our nice system, right? And then we have a 1 and 2 zeros, which would make this a C. We have a 1 and a 1 there. This is a D. Then comes a 1 here and here, but not there, which make this an E. And then we have all 1s. Make this an F. Okay, so now we have an exhaustive switch statement which takes care of all the different alternatives. And let's add a default down here. And if we get to this point, we will error out. So let's do an error, and let's have an error which is called bad instruction or something. I'm trying to remember what it's called in Linux and on Intel CPUs. Is it bad instruction or illegal instruction, perhaps? But bad is shorter. Let's do that. Bad instru. These variable names are already starting to get out of hand, big. And we should give the VM to this, right? Where do we have our error? VM and error code, that's right. So let's add this error. Define bad instruction is kind of long. If this is called segv, I think this should be called something like, let's just do error instruction. That's smart. And this will be 8. Yes. Okay, so what different things do we have here? Let's put here what we are doing. So in this first case, we are moving to AX. And then we have the binary thing. And this is what we are currently already doing, right? So let's copy this, or move this rather. And if we get this 8, we will set our AX to argument A1. Maybe we should create a variable for the destination. And we need some kind of destination type in that case as well, right? Well, at the moment we are only moving numbers. So let's make this easy for now. So we will basically have, let's see, let's use rank like I did up there, and let's say destination, or let's do in 16 destination. And if this case happens, then we will set AX to a destination, like this. And let's also update our example program because it's not correct at the moment. Or maybe it is actually. Let me double check one thing. Yes, we need to change this 3 right here, because now we're starting at 8. No, the move is 8, so we just need to remove this one. Too bad we messed up our nice looking thing. I don't want to. Yes, I do. Let's copy this and put it here. B, C, D. Okay, it's not as nice as we had it before, but it's okay. So we have move, which is 8, and we have 9 all the way up to 15. And then we have those 2, which should be above this, right? Oh, those pastes. There we go. Did I get it right? Think so. Okay, so this is what we have now. Which means I think we can run our program. Did I miss something? I didn't call it bad instruction. I just called it error instruction. And we also need to update our error function to print that error. This will just be error instruction. And inside of our error function, we want to add a switch. And let's use this one. And we'll have error instruction. This is this is illegal instruction, like so. And if we run our code, not now, 42. Yes, the semicolon. I shouldn't start with 8 here. No, I shouldn't. So let's go to that line and this is not the place. Right? Maybe, no. What did it say exactly? Line 80 in the C file. Here we are. Yeah, because move is 8, so this will go from 9. So we make clean, we jump down a little bit, clear the screen, run make, and boom, it compiles. And it runs. System halted works, but AX does not. Maybe we forgot one step. Yes, we did. Because we are using this, but we haven't really defined what it is. So the destination in our case will, for now at least, just be the int16 of, we have alias for this, the int16 of the first argument. That's right. And this will change. Let's mark that somehow. And now it works again. AX is 5. Okay, so now we are back where we started, but with a nicer structure, and we are able to deal with those different cases. So let's copy this line, and let's add this to every single one of those. And in this first case, we move to AX. Second, we will move to BX, CX, and DX. And maybe we should update those as well. So this will be moved to, and this is not EX, it's just AX. So this will be moved to BX, and this is CX, so move to CX, and this is DX, and then what? We might want to move to the stack pointer. Let's do that. So move to SP. We can't move to the instruction pointer. That doesn't make sense. In that case, we need to do a jump instead. So what shall we do with those we have left? Basically, we have 2 holes here. So let's just leave them for now. And we can even comment them out just to show that we are not yet implementing those. This. And what about this case? The 15 case where we have 3, let's move this to this one. When we have 3 ones, as we mentioned before, this would signal that we are not moving to a register. We are moving to a memory address. So should we handle that at this point? So basically this will be move to an address, and that's usually highlighted by putting brackets around. So that means that we should move it to this address. So how do we deal with that? We can't really deal with this at the moment, since we don't really have a stack which is working. So let's mark this as do later as well. But the other registers should be fine. So let's, for instance, see if we can try to move something into the CX register. And where do we have that checked? I think inside of the error function at the moment. This is very temporary though. Right, this thing. So let's select this as well. We need to change later on, but for now let's use it, and we will have the CX register. So if we run our program now, we should get a 0 there because we haven't done much to it. That's right. And if we were to modify our program so it is actually moving something to the CX, where would you do that? It would be here, example program, and our first instruction. In this case we set it to a move, but we need to set it specifically to the CX. So let's see. This is AX, BX, CX, which means instead of putting move here, we will simply put the opcode of 10. And let's signal that this is still a move. And this will be, let's see. So we have AX, BX, CX. And can we put a big number in there? I think we should be able to do that, like ABCD. It is a 16-bit register after all. So we will basically try to execute this instruction right here. Okay, almost. We did get 1 byte. What happened to the other parts? So let's see. Let's first see that we are doing everything correctly inside of this example program. So we are copying how much? VM program first instruction, and we copy the argument and how big. We are formatting it as an int8 for the copy function, but that's alright. And size is SA1. And SA1 is the size of the instruction minus 1, which should be 2 bytes. So we are copying it to the program correctly. What happens when we try to execute? So let's start at the execute function, which goes through the program in this loop, and it checks that we are not out of bounds. And we try to exec the instruction. And we do that by sending the VM, and we're sending the pointer to that point in the program. So if we check the execute instruction, we get a part of a program. And we switch for the size, which should return 3. I am setting 2 arguments if we have 3 bytes, but that's not entirely correct. We actually only have 1 argument, but it's 2 bytes. Which means this would probably never happen. Well, yeah, it's possible. But we should add a case though. Because we could have 5 bytes. And in that case, we want to do this. So we want to send both 2 arguments. But when we have 3 bytes, we'd only want to have 1 argument. So let's comment this out for now. However, that's not the problem we're facing now, because here we are setting the argument to the correct thing, I guess. So p plus 1, and p itself is the instruction. So if we have 2 bytes in the program for the first argument, we should probably get that into our A1. And what is A1? It's args. And what is args? It's a 16-bit thing, right? Yes. Type def in 16. Okay, so why doesn't it work as we want to? And we are sending the VM, the opcode, and A1 and A2. And the move instruction, it takes 2 argument types. And we are setting AX equal to the reg of destination. So we have reg, we have args, we have int16, and all of them are 16-bit, I think. Or yes, they should be 16 bits. But let's double check. So args we did check already, but what about reg? Type def unsigned short int, that is 16-bit. So why do we only get 8? Why do we only get 8? What happens to the first part, the first byte? Exec instruction sets the A1 and it's P plus 1. And that is correct. Because we haven't increased it or anything. No. So I can't see another possibility than that our program, that it doesn't get copied correctly into our program. But for the sake, just to make sure, let's add a printf here and echo out the 2 bytes. So it will be 0x%. We want 2 digits and it's an HHX. That means 1 byte. And one more of those, 0x%02 HHX. And an HX is a 16-bit and an X is a 32. I guess the H stands for half, so first we have it and then we have it. So, what shall we put here? P plus 1 is the first byte, and P plus 2 should be the second. So, if I am correctly analyzing this, we should get a 0 and then those CD things. I think so. Perhaps in the other order. Yeah, CD AB. We do get the AB at this point. But it does not follow along to here. That's interesting. What if we were to print the A1 at this point? So this will be 0x% and 4 digits, and this is just an HX. And this will still be P plus 1. Let's try it again. 00 CD. Isn't that a bit weird? Maybe I am messing up these Endian things somehow. What is P plus 0 at this point? So this time we had this 00 CD, and this time we have 00 0A. So this is the move instruction. But why does it get rid of 2 bytes? A1 equals this. And we have this right here. So, by the way, what do we have at position p plus 2? Zero, zero, AB. Okay, so let's see what we have here. P0 is 0, what was it? 0A, moved. P1, P1 was 0, no, P1 was CD, right? And P2 is AB. And if we give the 16-bit thing P2, then we get 0, 0, AB. Maybe it's how we're printing it. Could that be it? So maybe the values are right, but we are printing it wrong. But I don't really see that, but let's see. P plus 1 should be the right call, I think. What happens if we just do %x here? And let's select this somehow so we know which one to look at. No, only the CD. And if we do the same with P plus 2, AB. Maybe we need to do a cast or something. If we give this A1 and we specifically tell it to be an int 16, what then? Still just CD in this case. And if we give it P plus 2, doesn't change. Well, it's AB now and it was CD before, but the problem does not go away. What if we move this parenthesis here? Oops. Here. Will that do any difference? Nope. And what about P1? I wonder if I'm crazy or if it's a bug somehow in the printf function. Since we do have our 2 bytes, we showed that on the line above. What if we go back to Ajax? One is that thing. Maybe we shouldn't think too much about this P1 thing. Let's try to print this A1 instead. And see if we can modify that somehow. Okay, we're at this point. And we set this to this. If we were to we need to dereference this the correct way. So let's see. This is just a memory address. What if we do this? Could that make any difference? This might not even compile, but let's see. No. Right, because the address is not 16-bit, so we can't do that way. But we still wanted to reference it as a 16-bit thing, right? Not an 8-bit. But we can't do that either. It's always a little bit tricky with those dereferencing stuff and parentheses inside of C. Okay, this compiled at least, but same problem. Should we try this? Same thing. And if we were to do int32 or just int, would that make a difference? No. No, 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 no. What am I missing? Well, I need to figure out how to do this the nice way, but I will do it the ugly way for the time being. And how to do that? Well, I could just, let's see, you can set A1, which consists of two different things, right? The first is the leftmost 2 bytes. So basically we have 0x AABB. So let's start by highlighting those two, the two A's. And we can do that by simply, let's see, we take the P1 P1 is the A's, I think. Let's see, P1 and we do an AND operation with a bit mask of FF00. It will select those leftmost bytes or bits. When we have selected those, wait a second, P1 plus 1 we should have here. When we have selected those, we also need to push those 8 bits to the right. No, let's not do that. Let's just get those two the way they are. Maybe we need to rearrange them, but let's start this way. And what will we do with the result of this? Well, we want to add the other part to it. So basically just plus whatever we have inside of P plus 2. Something like that. Not the most beautiful way of doing things, but I think this will work. We might have to rearrange some stuff though. Yeah. So we need to take it in the different order, I suppose. So first we take those two. And then we add this. We still get the same result basically. Maybe we are why does this happen? We set A1. How do we handle A1 afterwards? We just send it to this instruction. And the destination is a 16-bit thing. We have the args. And we set the CX to destination value. To the wait a second. CX equals destination. Yes, and the destination is the first argument in this case. And we're using 16-bit things. Am I defining that wrong, perhaps? In 16. It does sound a little bit weird. That I can get those bytes and print them one by one to the screen, but putting them into one number seems to be very tricky somehow. So let's see. If we have AABB and we want to take P+2 with this mask, maybe we need to do what if we take these and then we shift them like this? And instead of plusing this P1, what do we do? Let's see, if we push those to the right, we should take no, I think I did this wrong actually. Or obviously I did it wrong because it doesn't work, but let's write this again. So we take the first thing, which is p plus 1. What was the result the last time? We got CD here and we got AB there, and that was AB what was we was plusing the first time. So let's say we have P1, which we AND to this mask. And when we have done that, we plus P1 again, and we AND it with this. Does that make any difference? Oh. This should be P plus 1. Okay, when we do this, we get to see the and if we were to do P2 at both those locations, then we get AB instead. So we get the AB. So if we were to take this AB shift it to the left, then we AND it to, no, not AND, we OR this to star P plus 1 and 0 FF. Something like that. ABCD. It took a little while, this, huh? And why is even this necessary? It seems so wrong that C cannot handle this for us. Probably we need some typecasting which will achieve this, but okay, this works, so let's keep it for now. I don't want to spend one more second at this. And if we were to have two arguments, we will do this twice. Fun stuff, huh? So the A2 in this case, this would be P4 and this would be P3. And the rest is the same. In case 2, if we have 2 bytes, we don't have an instruction for this yet, but if we have 2 bytes and one of them is the move, then we have 1 byte left. So this would probably mean that we are moving to the higher or the lower half of the AX register, for instance. And in this case, this would be appropriate because obviously we only get a byte when we do this, so let's keep it for the 2 bytes. Okay, so now we can move stuff where we want it when talking about registers. So what is the next logical step? That would be moving things to the memory, but we don't really have a memory at this point. But yeah, that will be the next step, dealing with the memory. What's up, guys? Welcome back. Now I think I understand why this happened. I'm not going to change anything at this point, but I at least want to explain. We are dealing with 2 different types of endian. So basically the byte order, because when we did our example program, let's see where it is. What we did was this: A1 is equal to 0x ABCD. And how does ABCD like that look in memory? Basically, it puts it into, if we take byte by byte, it puts it into this order. But when we are copying it, we are basically reversing that order, since we do this byte by byte. We do not copy it as an int16, we copy it byte by byte. So then we get ABCD inside of the memory instead of what we should have. So basically, if we try to grab at this, we will simply get the CD, but with zeros. Or the zeros will be here. And if we try to grab this AB thing, same problem. but then the zeros would be here, I guess. So basically we need to take that into account when dealing with those 16-bit numbers, that we need to switch position of them inside of the memory. Alright, at least we both learned something today. Okay guys, welcome back. Let's continue with our virtual machine. So before the break we made our other register work with the move instruction. So now we are able to move stuff into the AX, BX, CX, DX and SP. Yeah, we're not gonna move anything into the IP though. Alright, so let's see, what's the next logical step? Well, we haven't really covered all the registers as of yet. Well, we do have these 16-bit registers, but they have their 8-bit equivalents as well. So the AX is 16-bit, but then we have the AL, and L stands for low, which is 8-bit, the lower 8-bit. And then we have a high, which is also 8-bit, and that's a higher 8-bit. And when I'm talking about lower and higher, let's say we have a 16-bit binary number. So let's say we have 10, 11, for example. So basically 10, 11 is the value of AX, but AL has the value 1, 1, and A high has the value 1, 0. So you can use that in order to target specific parts of the register, and that can be very necessary in some occasions, because you do want granular control. And so how do we achieve this? We could do more of the same as we have done. We switch by the opcode, and we have different variants of the move instruction with different binary bit patterns and so on. But we are already occupying all the way from opcode number 8 to possibly opcode number 15 with the move instruction. So, well, we could say that we want another bit, for example, that we want to use for the move instruction, but I don't want to do it that way. Instead, I'm gonna add one more register, because there is one register that we haven't talked about, and that's the one called flags. So basically, flags means that if we have a bit value like this, that means that this first bit has a Boolean value. So that means that something is true or false. And same with this next one. That has a different meaning, but still a Boolean value. So we can put 4 different Boolean values inside of this register. And usually there are stuff like the 0 flag, which means that if we do a mathematical operation and the result is 0, then the 0 flag is set. And it's also being set when errors occur and when interrupts or similar needs to report back. So that's one way. There's also the carry flag, which works like when you do a mathematical calculation by hand, you put the little number on top, and that's the carry, which is denoted by this flag. And we do also need something to use with comparison. So if you, for example, want to compare the AX to number 5, what happens then? We need to store the result of the comparison somehow. Is it equal? Is it lower? Is it higher? So we need a flag for that as well, and possibly other stuff in addition to this. So let's see, we have these 4 flags. What should we do? So let's say we have position 1, position 2, 3, and 4. And we need to first occupy the most important things, and that's the comparison. So let's say we have an equal register. So if this AX is equal to 5, then this flag will be set. But we also need to take account of the less than and greater than, which means we need some kind of less than or greater than flag. We do only need, since we have an equal flag, we do only need one of those. So let's do greater than for this flag. And let's see, what else do we need? We might need the carry flag. I'm not sure if I'm gonna do it like that though. But let's put this in parentheses, and then at position 4, no, let's remove this entirely, because I need both position 3 and position 4 to do my move stuff. So I need to be able to decide if it's the high or the low register. So let's have a high flag and a low flag. If both these are set, we should make an error out of it, because both should not be set at the same time. That basically means that we need to unset the flag and then set the other one. So if the high flag is set, then we are only affecting the high part of the register. If the low part is set, then we are only affecting the lower 8 bits of the register. So let's add this to our registers. So we create a register called flags, like so. And do we need to initialize it somehow? Let's see how we did it inside of the virtual machine. I think this is the one. We are allocating and we are zeroing everything. Okay, that's good. So let's see, I think I'm gonna take this thing and move it down here. No, like this. Maybe I'll do it like this instead. Okay, so now we have it a little bit easier available. Maybe I should move this in one step. Yeah, that's better. Alright, that's a different flags. Maybe I should add some explanation as well so I don't forget what they mean. Equal flag is this. This is greater than flag. This is higher. What should we call it? What is it? It's a higher part of the higher register. And this is the lower part of register. Maybe I'll come up with a better word. Alright, so that's our different flags. And maybe we should create some kind of macro to make this a little bit easier to deal with. Let's see, where are our other macros? I think I create, right here. So let's start by creating one of those for flags as well. Like so. We'll probably never use this though. But what we do need to use, and maybe we should put this on its own thing here, because let's copy this, by the way. 4, 5, and maybe I should do this. Conserving space. So 4dd paste, and we go up here, paste. And this is just temporary, so I have them available. So how do we do this? Let's define an equal macro. And no arguments. So what will this do? It should check the first. I need to have a bit pattern here, I think. 10, 11. And we want to get at the first position, which means we should take the, let's see, we need one argument, by the way, the virtual machine, right? So we take the flags of x and what do we do with it? We need to do some binary bitwise operation. First, we want to mask this one. So we need a mask that looks like this. And what would that be in hex? Let's see, this is 1, 2, 4, 8. So if we were to add this to 8, then we end up with this. Now we need to push it 3 bits to the right. So let's add a second parenthesis to make this explicit, and we push it 3 bits to the right, and then we have the value. And let's make this an explicit logical operation. I wonder if it's possible to do like the JavaScript double bang thing in C. I have never tried that actually. But logically it should be possible, I think. Alright, so this is equal. Let's create 4 of these. The next one is greater than. And in this case, we need to do basically the same, but this time we want this bit. So this is 1, 2, 4. So let's add this to 4, and this we only need to push 2-bit positions. Right, let's move on. This is the higher. And this will be 2, and this will be 1. And then at the end here, we will have the lower and this time we will end it with 1, and we don't need to push it anything at all. I removed the wrong thing here. I need to have this parenthesis and this. Yeah. This should do it, I think. Alright, I have no clue if this actually will work. So let's try it out then. How do we do this? We need to set that register somehow, and we do not have any move instruction or similar, which makes it possible to do that. But we can't set it manually. So if we put an 8 in there, we should have the highest of the flags, the equal flag. And we can remove this now. So let's set that register to 8. And where should we do that? Well, I guess we can do it inside of our main, right? So here we have this. We execute. We print some hex. Let's see, when we are done executing, we remove the virtual machine, so we can't really do it inside of main. We need to do it, let's put it inside of the execute function temporarily. We will want to remove that eventually. So let's see, we can put it here, right? So what we should do is we should take the virtual machines flags register and set that to an 8. And then I want to do a check if equal, yeah. So if the equal flag is set, we will print e flag set. Otherwise, e flag not set. Let's be very explicit today. Alright, let's see what happens. So we make and we run e flag set. Who knew? It worked with double bangs and everything. That is pretty remarkable, I think. So let's just double check. If we set this to 4 instead, will we still see that flag? Not set. Beautiful. Beautiful, beautiful. And let's try one of the other ones as well. We can do this and this and this. And let's set the greater than. E flag not set, greater than flag set. Okay, it works. Very nice. I think I will keep this, but I will remove the else clauses. And I will of course remove all of these when we're done. But it's good to have those as a debugging kind of thing. Right. Okay, so now we have a way to signal to the move instruction that we are not talking about the whole 16-bit of AX. Sorry, the whole 16-bit of AX register. We are only interested in the higher or the lower bits. All right. So where do we do this? Inside of the move function, I guess. And how is our switch function working? We are setting the AX in this case to this value. And I think, well, however we choose to do this, it will not be very pretty. So let's just put it inside of here. Yeah, I guess so. So it will be in the if statement, and I will check for the higher bits with the highest precedent. So if the higher flag is set, then we will take the VM and the, let's see, what do we want to do in this case? We do only want to deal with the 8-bit value. So maybe we should have a separate destination for that, like in DST8. And what would that be? DST8 should be equal to the A1 argument, but not just. Let's see, what do we have in this case? So we have like 10, 11. This is the whole value of the register. And we want to get at, no, we can't name it 8. We have to do one for the lower and one for the higher. So the lower would be this, and we want to get at this thing right here. So let's do an AND operation, and a 1, 1 is a 3, right? So if we just AND this with a 3, we should get the lower 2 bits. And how do we do with the higher ones? Then we are in the reverse case. So this is the mask we should use. Let's start there. So we have the value of the A1 argument, and we add this with, let's see, 1, 2, 4, and 8. That's a 12, right? So what do we have? We have 10, 11, and 12. Okay, so now we have those, but we still need to push them 2 bits to the right. And I know I'm overusing parentheses, but I think it makes this a little bit more explicit. So 2 positions, like so. Alright, so now that's divided. So if the higher flag is set, we still want to alter the AX register, but we want to set it to the reg value the reg value of DST high. And else, if we have the lower set, in that case we want to set the AX to the register of destination low. Otherwise, we will do this. Alright, so let's copy this thing. And we will put it right here. Let's remove this. And this will be dx, dx, dx. Okay. Let's do all the copy paste first. So this is what we want. And we want it right here. And we want it right here. And should we do it for the SP? I don't see why not. We want to remove this and this and this. And this one's done. Here we are dealing with the CX register. And here is DX, DX, DX. And then we have SP, SP, SP. And we don't want to do anything like this with the IP, and we don't want to do it with the with the flags. We will have separate instruction for toggling the flags, probably 1 instruction per flag. Alright, so let's see. Let's create some instructions for those things. So we'll start by going to the this one. So what do we have here? We have the nope, we have the halt, and we have the move, and this goes all the way to 0f, which means the next position would be 0x10, so 16. And what should we call those different things? And should we have an instruction that sets it, and should we have something that unsets it, or should we just have a toggle? I wonder how Intel does it. I know there is some flag or some instruction for setting the carry flag. Can't remember. So let's see. We are dealing with 32-bit Intel x86 assembly, and we are interested in set carry. And I'm looking for my favorite website, which usually shows up pretty high. Maybe I shouldn't have this. Maybe just like this. There, Felix Coutier. This is a good place. Alright, so STC, set carry flag. Simple enough. And it has a single 1-byte opcode like this. No arguments. But how do we unset the carry flag? STC. Could it be UTC, perhaps? Or CTC, maybe. No. Unset carry. CLC, alright. Clear carry flag. Let's double check with Felix. Yeah. Alright, so we have what was it? STC. Set carry flag. Set carry. STC. Set carry. Clear carry. Okay, so how would we name it if we did it similarly? We would have something like set equal, no, set equal. And then we would have clear equal. But what would the other ones be? We would have something like set greater than, clear greater than, and then set higher, clear higher, set lower, clear lower. How does this look? It's an awful lot of different instructions, but maybe that's not bad. Actually, I think we'll do it this way. So this would be 1, 1. This would be 1, 2. 13. 14. 15. 16. 17. And maybe we should have some reserved. Because that way we know that if it begins with 1 and this position can be different numbers all the way up to 9, then we know that we are setting different flags and stuff like that. So I think this is good. And we don't really need to have this explicitly in the code, but I still think we should do like this. Alright, let's implement all of these instructions. So let's start with this map. So let's see. We will have set something and it'll be 1 byte. And then we will have clear something, which will be 1 byte. So we have the equal, greater than, lower, higher, and then we have equal, greater than, lower, higher. Looks good. What else do we need to change? We need to go into the execute instruction. So this is execute, which executes the program, but we are interested in the exec instruction. So first we switch for the size, do stuff depending on that. Basically, we deal with the arguments. And then we switch for the instruction. And then we run different functions based on that. So, how do we do this in the best kind of way? We will have a case for set something. and then we will run the function of set something, and we will pass the VM, and let's pass the opcode for the sake of to make it look the same as the other ones. We do not need any arguments though. But do we want all the instructions to have the same signature? I think that would be good, but do we have a value for A1 and A2? Yeah, there's 0 from the start. Let's pass them. It's better to have the same standard for all of them. So we will have A1 and A2, and then we'll break. We will have 4 of those. And then we'll have clear something. And we run clear in the same way. So we'll have equal, greater than, higher, low, lower. And we'll have equal, greater than, higher, lower. And we will have the same here. So equal, greater, higher, lower. Equal, greater, higher, lower. Alright, that's easy enough. So let's define those functions. So let's start with set equal. We'll have a VM over VM. We will have an opcode. We will have args A1 and args A2. And the only thing we are going to do is what exactly? We need to define the register flags, and we take the current value of the VM's flags register, and what do we do with it? We want to OR it with an 8 in this case. And maybe we don't need an intermediary variable. Instead, we could just do VM flags is equal to VM flags, so we don't even need to do that. We can simply do OR equal to 8. And this will be the same for all the sets. The only thing that differs is this part. So let's copy this and do 4 pastes. Okay. that's not really what I wanted. Let's do 3dd and 4 pastes. That's better. Okay, so what do we have here? We have E, and we have G, we have high, and we have low, and we have 8 here, we have 4 here, and which one is 2 and which one is 1? Let's see. Position 3 is the higher one. Yeah. So it's like this. And how should we do with the clear? If we do like this, and we paste, and we do clear equal. So how do we clear this thing? We want to do the opposite, but is it enough to do just this? I need to see it in front of me. So let's do this temporarily at least. So we set flags equal to VM flags. And what do we have? Let's say we have this. And we want this first one to be a 0. So flags will be equal to flags. We will run an AND operation, but what value should we use? Basically, we would like to do something like this. Because if we AND with this thing, we will only affect the first position. But how do we know that we are going to use this? What if we were to AND with 0, 1, 1, 1? If we were to AND with 0, 1, 1, 1, we wouldn't mess up those 3 things, but we would definitely remove the first one. Yeah, that's probably it. So we would do an AND equal. But we will AND equal with this value. So we have 1, we have 2, we have 4, we have 8, and it's 1 less than 8. So it's a 7. out riding a bicycle, as we say in Sweden? Or am I doing the exact right thing? The line between geniosity and insanity is very thin indeed. Well, let's do dd and 4p. We have the equal, and let's assume that if we do greater than here, and the old value was 4, so it's probably one less, which will be 3. And then we have the high value, which probably is 1 then. And finally, we have the low value. And we can't really end it with 0, can we do that? It doesn't really. No, I think. So 7, 3, 1. What's the bit mask for 3? So 2 is this. So it's basically this. So we have 0, 0. And if we have this bit set, yeah, we're zeroing it out for sure. But what about this thing? Don't we remove that as well? And what would be the alternative? It would be this. And what is that? So we have 1 and 2, that's 3. And then we have 1, 2, 4, 8. So 8 plus 3. So we should have 12 here. I'm not sure, this doesn't really seem right. So we have 10, 11, 12. And in this case, we want to grab this flag. So the inverse would be 1101. And what's that? This is 1, 2, 4, 8, and 4 and 8, that's 12 plus 1, 13. So we have 10, 11, 12, 13. I don't feel very comfortable about this. And what about this last thing? Here we want to grab the rightmost bit. So the inverse would be this. And we have 1, 2, 4, 8. And here is 16. So basically it's 2 less than 16, it's 14. Do DE. So this would be it. We would end it with 7 and then C, D, E. Let's double check this one. So we have this bit, and the inverse would be this. And we have 1, 2, 4, 8, and this is one less, which is 7. I think we need to test this thoroughly. And not just assume that it works. And we have code for checking 2 of the flags, the E flag and the greater than flag. So let's say we start with all ones, because I'm most insecure about declaring instructions. So let's see, we execute. We want to go to the virtual machine thing right here. So we 0 everything, but then we want to set the flags register to all ones. So -1. And then we want to clear the equal, and we'll do that inside of our program. So let's see, how do we do this? I3 O is equal to halt, and then we copy this. So let's create another one of those. This will be I4. So we'll do P++. We'll set I4 O equal to clear equal. Then we copy into P value of I4 1 byte. Alright, so let's try this thing out. Oh, that's a couple of errors. Declaration of functions. Did you mean st? Okay, I did only do one. And I'm not sure if you know that, but it's very not allowed to have one underscore in front of the function names, because that should be reserved for GCC internal things and so forth. the code will compile, but you are breaking the standard. 37. Yeah, this should definitely be a semicolon. It's not very many errors today. I shouldn't have jinxed it, right? Segmentation faults. So I did something wrong with the copy, perhaps. I didn't change a lot of other stuff that should be able to cause this, right? So where is the function which deals with the example program? Right here. I for O equals to this, and then we copy, but did we make room for it? Probably not, right? So, right, we need to allocate for this thing. So I4 is also equal to the instruction of malloc S2. And let's also 0 I4 with the size of S2, which is 1 byte. And this time it'll go much better. Alright, so the greater than flag is set, but not the equal flag. Exactly as we were hoping, right? Let's try the other way around. So instead of clear equal, we want to clear greater than. Greater than flag set. Is this one of these days where everything just works? Because we had a couple of days in this series where nothing worked and we had to troubleshoot for hours. And today everything is just flowing. It's like you're in water, right? And you just float on top of the water. It's pretty remarkable, actually. Alrighty. Let's see if we can set those things as well. So let's see if we can set the equal. And we can zero everything from the beginning. So this time we should get the equal flag, right? Did we save? I think we saved. Did it disconnect? It did not disconnect. It did not. Let's try again. Save. We go here and we make clean, jump down a little bit, clear the screen. We run make, and we run the program, and boom. No! Why is the greater than flag set? Did I mix up the instructions somehow? Set equal. And how does this look? ST E, or sit with 8. And we have 1, 2, 4, 8. So it's this position. So why do we get the greater than flag? That doesn't really make sense. Everything went too easy today, and now it's crashing and burning. Let's check the execute instruction. STE runs STE. What happens if we do STG instead in our program? STG. This time the greater than flag should be set. And it is. And if we were to, let's see, let's do this, and this, and this, and let's say we have an R5, which clears this flag. And we need to allocate for this as well. So this time we shouldn't get any flag set. Oh, maybe we need to create the variable as well. Greater than flag set. It's set no matter what, it seems. It's carved into stone. Let's see. Execute instruction. And we have move. And where is our halt code? Move. We have exec instruction, move, halt. Okay, we run error. Here, and if greater than GT flag set, let's print the value. Wait a second. This shouldn't be here anymore. Awkward. Okay, so now we have no flags because we do a set on the greater than and then we remove it. So now it looks right. Let's see. Let's set the equal flag and then clear the greater than flag, which is already cleared, just to make sure that that doesn't mess up anything. The equal should trigger, right? Because we set the equal and we clear the greater than. What if we were to do set equal, Still nothing. Let's print the value of flags as I intended. Let's just find this arrow function right here. And instead of cx we do flags. Flags. Okay, so flags is all zeros. Flags is all zeros. What if we were to set the greater than? And it's not like the problem last time that I had already freed the virtual machine and we were troubleshooting like maniacs. Let's see. We printed the system halted, set exit code, print the value of the register. And then we free virtual machine down here. Let's try the other way around. If we go to our virtual machine function and we set the let's see, the p flags to all ones. Let's start there and see that we trigger this thing. Alright, so now Now we have the equal flag and the greater than flag. And as we can see, it's all ones. And let's go right here and we clear the greater than, we clear the equal flag. So now we should only have the greater than. We still have both. It's like those instructions aren't executed. So let's follow it from each step. First we have the execute function. This one. And this simply goes through the instructions one after another. Let's go one step earlier even. In our example program, where do we copy everything? We copy to P. And what is P? It's a program pointer. Do we allocate that anywhere? P is equal to the memory of the VM. And then we copy things to it. So how does it know how long the program is? Execute. It doesn't know. It just right. It executes all the instruction one after another. But when it reaches the halt, what does it do? It halts. Of course, but of course. Sometimes it is very helpful to take a step back and go one level above in the function hierarchy and really try to understand what's going on and in what order. So let's do halt as number 5 instead. And we can set the greater than, sure, but what I want is to clear the equal. Because here we had it and we shouldn't have. And now we don't. Very nice. So let's see if we can set stuff as well. So this time I want to set the equal. And let's try clearing the greater than. Or maybe we shouldn't only use those. Let's try the lower instead. Right. So, right, we should remove the -1 thing here. So So now the register will start at 0, and then we will set the equal, and we'll clear the lower, which is cleared already. And we have the A flag set. Ladies and gentlemen, everything is working as intended. Isn't it nice? Isn't it beautiful? Beautiful. So let's just see if our move works as well. So let's move something into a high. So let's start by going to the error function, and this time I want to print AX. And let's go to our program, and what do we have here? We have a no up, and then this and this, and we have a halt, but we start out with a move instruction. What I would like is to have something before the move. We set A1 to 5. And that's CX. So let's set this to 3 instead. That should be the AX register. And let's set the higher flag before all this. So let's create. It's not very pretty with all of these temporary variables, but this is only an example function, so it's okay. So I0 will be equal to the instruction of malloc, and this will be S2 size. And let's clear this out. Alright, so we'll set I0 all equal to set higher. And we'll set P equal to the V and M. And we copy into the P value of I0 to 1 byte. And with P++. And we do this, and this, and this should not be. Okay, I think this is right. So we set the equal, we clear the lower, we halt. Okay. Let's see what happens. AX is 0. Am I altering the wrong register perhaps? Let's double check what the different registers and their values or identifiers. So let's see, in order to get to AX we should have an 8. 8. And what do we have in our example code? If I can find it here. Let's see. Move. Okay. This is the one. And what's the value? My memory is like a goldfish. That's the burden of getting older, you know. AX, where art thou? AX. Here it is. 8. Okay. 8, 8, 8. So our I1 should be equal to the 8. And what are we putting there? We're putting a 3. And where are we putting it? So what do we have? We have those bits, and a 3 is 1, 1, and we want to put the 1, 1 in our higher. So we should have this left. And we have 1 and 2, and this is 4 plus 8 is 12. So if I have calculated this correctly, the AX should be 12. And it's still 0. I still think we're doing something wrong with the program. I0 is this, and P is this. We copy to P, I0, 1 byte. We move one step further, and then we have this 8, which should be a move to the AX register, I believe. We calculate the size, set the argument, but it's weird that it's 0. If it was set to 3, I would understand, but it's odd that it's 0. Let's see if I'm printing the correct register. If we go to the error function again, AX is equal to this. And because I know that the move did work before. So we switch on the opcode. If it's an 8, we affect the AX register. And if higher, we set to this. If lower, set to this. Otherwise, we set to this. It looks okay. It sure does. What we could check is if instead of setting the high, we were clearing the high, would it make a difference? Okay, it does. So something is wrong with our calculations for higher, lower. Interesting. Let's try setting the lower. Does that work? Okay, that works too. So it's specifically the higher that is the problem. So we set this to higher. And let's double check how we deal with that. So let's see. It's in the move function, I guess. So how do we do this higher thing? We take the argument, we AND it with the C, is that right? So we have those 4 bits, and we want to get at those 2. So this is the mask we want. These 2 doesn't matter, but we want this. And what is this? So we have 1, 2, 4, 8, that's 12. And we have 10, 11, 12. So we are ANDing it, 12. And then we push it 2 bits to the right, which should give us this position. But that's the source, right? Right, we are trying to take the higher bits of the source. But the destination is the interesting thing here, right? Because the AX should be... Right, so I think this actually works if we supply it with a value which actually has something in the higher part of this, of these bits. So let's see if we go to our example program and we're giving it a 3. What is 3? It's this. And what if we wanted to have this instead? And what is this? This is a 12, right? So if we set the 12 here, 0, 10, 11, 12, then I think it will work, because it will take the higher part of the source and put inside of the higher part of the AX register. And I'm not entirely sure that's what we want, but it works. Three. Interesting. So it takes the higher bits of the source and puts it into the lower part of the destination. And I think we want the other way around. Let me suck a little bit on that caramel, as we say in Sweden, and I will get back in a while. Did you learn anything useful today? And do you want to support this channel? Go to drbirch.com/support. You can also click the button Become a Member. Thank you for your support. Alright guys, welcome back everyone. So, I want to do a couple of changes. First of all, I want to rename my virtual machine. And if you remember, I had a post in the community about getting good names. So, just 1 second. Need to find the correct one. So here are a lot of different suggestions from you guys, and I got some very good suggestions, and it basically came down to 2 contenders. There was, let's see, this one, Bitrich, really good one, and there is one more. I think it was pretty early. Here we are, Bird Nest. I like that because of the penguin, Gunter, you know. And since Bitrich is already in use by a lot of different software, I've Googled it. Probably Bird Nest too, but not to the same extent. Plus, I really like the name Bird Nest. So this is the one we're gonna use. Thank you a lot, Mike. So let's see. I don't want to rename all the files and do all that messy stuff, but I will, however, change the top here to bird. Should it be bird nest or bird's nest? It's messy with those, I don't know what it's called, those kind of things. Fnuttar, as we call them in Sweden. Bird nest is good. So we save this one and we will go up here. Bird nest, and let's remove that. And also in the make file, what I want to change is the final binary. I don't want it to be birch VM, hideous name. I want it to be bird nest. That's pretty good. And then we can call the different virtual machines for birds. My little birds. Alrighty. And thank you everyone else for your very good suggestions also. Everyone I got, I think, was a valid contender actually. Alright, so let's see. Bird nests we will create, and let's remove the other binary. Which we run it clean, and we probably need to update that as well, right? I just did. So make clean. Looks good. We run make. No. Right. We need to change this little thing as well. Alright. Now we have a bird nest. Okay. So what if we got some actual coding done as well? Last section or episode perhaps, I haven't decided how I'm gonna divide the different content yet, but we did create a lot of small instructions like set the register and clear the greater than and stuff like that. And then we have the high and the low E flags register. Yeah, you know all this stuff. So the only thing we really didn't get to work was when we move data to the higher register, then we are taking the higher part of the source and putting it in the lower part of the destination, and that's not what we want. We want the other way around. So let's see. First I want to just alter this example program. I want to move not an 8. Oh, that's a move instruction. Let's see where this is the argument. Okay, I don't want this C. I want to move something with using these 2 bits right here. So let's say we do a simple 2. I think that's a good enough example. Alright, so where is the problem? The problem is inside of our move function, because all the different register parts looks like this, and this is not right, because we are grabbing at we're talking about the source value here, and the destination is what is interesting. So I think we can safely remove those extra variables right here. Let's remove those 2. And then we are going to change basically all of this stuff. So let's clear it out a little bit. all the different, maybe I shouldn't, yeah, vmcx equals reg. I was thinking if I should keep one of them so I have a reference, but I think I'll remember. And SP is pretty easy. I decided that I don't want to use any registers with this. I mean, I don't want to move to the higher part and lower part of SP. There is only one move to the SP. So I will even do this if, let's see, if higher or lower then we will error. And we want to send an error instruction. Is that the only argument to error? I don't remember. Error. VM and error code, right? So that's what we'll do, and otherwise we'll do this. And the break should happen anyway. Alright, so we can't move to the higher or the lower part. The only thing is the actual SP as a 16-bit register. Okay, so let's see how we should structure this. Let's say we have value inside of AX, and we'll do this in binary. Let's say we already have this value inside of AX, and we want to do move to AL. We don't do move to AL, and I'll type this in binary first. I want to move, well, I simply want to move a 1 to the A high, actually. Okay, so a 1, that is actually a 0, 1 then, right? And we want to move this to this part. So what will that mean? Well, we want the end result to be a 1 here instead of a 0, 1. And we want to keep the other one because we are only doing stuff that affects this register. So we want to replace the entire 8-bit value. That's well, actually I think I've been grabbing at this a little bit wrong. This theory is still valid, but this is a 16-bit register. It has quite many more of these ones and zeros. So I hope I didn't make any problems with the flags register because of this. No, I didn't, but I do have 4 more bits to use. Anyhow, we still want to move a 1 to the higher part of the stuff, and this is this at the moment. So basically we want to change AX in this case to be 0001 because we're moving a 1 to this part of the register, and we want to preserve this one right here. So how do you do that? If we were to use some intermediary stuff, we would, for example, do something like, let's say we have a value x, we set x equal to the VM's AX register, but we don't want to grab at everything. What we are interested to preserve are these 4 bytes, these 4 bits, lower 4 bits. So half a 8-bit register. No, I'm doing it again. Half a 16-bit register is 8 bits. So we need to mask 8 bits. So actually there are a couple more zeros and ones here. It's too big of a number, I think. 16 different ones and zeros to keep in my head. Anyhow, so we want to mask this like so. Maybe I should do it in hex. It makes it a little bit easier. So what we have in this case is 0x AABB, where the 2 A's is 1 byte and the 2 B's are 1 byte, and we want to grab at the B's. So that's why we mask them like FF. And if you don't understand any of this, please watch my binary operations video from a couple of weeks back. I explain it very thoroughly. Okay, so now we have the intermediate value x, which has what we want to keep from the AX register. Now we want to add our stuff from the move argument, but we want to move it to the higher part of the register. So I will do it in intermediate variables first, and then I will probably move them off. So let's say y will be, we take the value of the AX, or no, we take the x value, because that contains the thing we wanna keep. So basically we want to plus this with the A1. A1 is the argument. So let's see. We want to take the argument and we want to push it 8 bits to the left. So this is the register, and we want to, let's see, we want to push it 8 bits to the left. And then let's OR it with the x value, like So I think this is the right way to do it. So how can we do this a little bit nicer? Well, we can take this parentheses and replace the x. And let's change the order. This is confusing. So we have the value of the first argument, a1, pushed 8 bits to the left, leaving 8 bits to the right to be used. And we want to OR it with the VM value ANDed with 8 bits of ones. That should be the... What should that be? That should be the new AX value. Can we do just VM AX equals, or do we need one intermediary variable? I don't see why not, actually. The important thing is to have the parentheses lined up, which I don't. Now I do. So let's see, we do this stuff, and then we OR it with the current value and it with FF. Yeah, seems about right. However, this is the one case. This is the case when we have when the higher is set for that VM. Forgot the values here. So this is when the higher bit is set, then we should do all of this stuff. But what should we do? Let's see. What should we do if the lower bit is set instead? Should we make any changes? Well, we should basically do the same. The only thing is we don't need to push. The difference is we will not push this thing. We will, however, need to push this thing, because now this time we want to preserve the higher bits, which makes it a different mask. Let's see, the A1 is the A1 in this case. We still take it from the lower bits, but we want to preserve them as lower bits. And in this case, we want to OR it, so we grab at the leftmost 8 bits. So we preserve the higher ones. And then we don't need to do anything else, I guess. Because when we OR it with this, this kind of goes from lower to lower. And this will be the AX higher bits. Yeah, I think this is right. And otherwise we will do it very simply by setting AX to the reg value of A1. Okay, this time I think we got it right actually. Before we copy paste this stuff, I want to make sure that we don't have both of these set. So I don't want this check right here. No. I want this to be globally for everything here. So the first thing we're going to do in the move instruction, almost, is we're going to check if the condition higher for this VM and lower this VM. If this is true, then we want to error this VM with the error instruction. Simple enough. And there might be instructions where this should be a possible combination, but not the move instruction. Alright, so we'll take this stuff and we X and we P, and let's paste this in and we paste it in. In, and that's good. Let's see, AX we have here we have BX, we need to change those three, but also these two. No, not AB, this should be BX, right? And BX. Okay, so 5 places per. So we have AX, BX, and finally we have the DX. Like so. And now I believe it will work. It will work. Would you look at that? Let's try moving a 1 to this register first, and then move the 2 up here. So we really see that the value is preserved as well. And we need to create a better example program function, because it's very messy to insert instructions when I want to test stuff. I think that will be our next stop actually. So let's see. What are we doing right here? We are entering a set high, and then we do the move. To the, I believe this is AX, right? No, not anymore. This becomes A high, right? So we want to move the one to AH. No, we are changing the wrong thing. This should be an 8. So this is the right one. So the 8, this is the move instruction to the AX, and since we have the higher bit set, it will be A high, and I want to move a 1 there. But I would like to have a regular move 1 instruction first. What would happen if we just copied those 2 first? Let's see. No, we can't do that. Let's cheat. Just this time and just this example. We'll set AX to 1 from the start, and then we will do all this stuff. Would you look at that? It preserved our 1 and it moved a 2 to the AH, the higher part of the AX. Beautiful. Beautiful. So now we have basically done what we were set, the task we set for today, and that was to create a move instruction when moving a value to a register, and it can be one of the general purpose ones, it can be the SP, or it can be the higher and lower parts of the general purpose registers. And in order to implement that, we created a flags register, which and a couple of instructions which used that part. Yeah, I think this should be it actually. I have recorded somewhere around 4 hours of material, and I believe that is a good enough second episode. I would say maybe it would be 3.5 hours after post-production. So, thank you for watching. I hope you liked this episode. And if you want to grab the next ones, please like and subscribe if you like this one. And we will see each other very soon. Take care.